Greetings everybody. Let's take a look at our three-part series on Green's theorem. And so just a little bit of a reminder that when we were talking about these vector fields and kind of line integrals over them, we had three topics or three concepts that were really running around. The first one was that our vector field was going to be conservative. And remember, all that meant was that the vector field was going to be the gradient of some potential function. Then we had path independence that just basically said if we did the line integral over between two different points, that it didn't really matter what path we followed, we were going to get the same answer no matter what. And our fundamental theorem of line integrals gave us the connection of saying that if you were conservative, then you were really going to be path independent. And if you had a vector field that was path independent, then it was going to be the gradient of some potential function. And so that was our fundamental theorem of line integrals. But we didn't really necessarily want to come up with a possible potential function in order to see if something was going to be conservative. We wanted some kind of more simple calculation that we could make. And for that, we came up with the curl of the vector field. And so if we could talk about the curl of the vector field being 0, that's what we meant by saying that that vector field was going to be irrotational. And if we were conservative, then Clairaut's theorem actually gave us that a vector field was going to be irrotational, that this curl was going to be 0. And so now, if we've got something that's irrotational, can we get back around to path independence so that all of these things really end up being the exact same thing? Well, the connection between irrotational and path independence is made by Green's theorem, but it's got a little bit of a twist in the middle, and so we'll fill this in with maybe a little extra condition here in the next few videos. So what does Green's theorem say anyway? Well, if we let C be a positively oriented, piecewise smooth, simple closed curve in the plane, and we let D be the region bounded by C, then if P and Q have continuous partial derivatives on an open region that contains D, then our line integral over this simple closed curve, so remember that little circle was saying that we're doing a line integral over a closed curve. So our line integral over our closed curve C was going to be equal to partial q partial x minus partial p partial y dA. So we'll kind of recognize this as being our curl in this case. So we've got this connection between an area integral, so a double integral, and we pull that back to an integral on the boundary. And so that's kind of what Green's theorem is saying. Let's see and kind of dissect this a little bit more and kind of understand what all of these pieces are actually talking about. So we can really think about, instead of starting with C and looking at the interior, we can really imagine that we're starting with some kind of region D. And that region D has a boundary on it, and that boundary curve is going to be and that boundary of D is actually what we're going to mean by our curve C. And so kind of notation that we have for that is that C is equal to kind of our partial derivative symbol on D. It's not really a coincidence. It follows a lot in here that we're kind of using that symbol to mean a lot of things, but we're really saying that it shows up in Calculus 3 when we're talking about partial derivatives and vectors. So that's kind of where that's showing up at this point. And so what do we actually mean when we talk about the boundary of a region? Well, we can say that a point is on the boundary if we can put an open ball around it, and that open ball is going to overlap and contain points of D, but it's also going to contain points that are not in D. So you're right there on the edge. You get both. You get some of the inside, you get some of the outside. And kind of, again, this notation that we typically use for boundary of a set is this partial derivative symbol applied to this set. So we're not really taking any derivatives. This is just a symbol to talk about we're dealing with the boundary. And so we've got a region D, and then we know now we've got an idea of what the boundary of D is. And so a curve C is equal to the boundary of D. And this curve C, what we need is that we can give it a parameterization by smooth functions. So we can take as many derivatives as we want. Everything's going to be continuous. And we can do it in a finite number of pieces. Now that's really what we mean when we were saying that we had a piecewise smooth curve. So we've got this region D, we look at the boundary of this region, and that boundary of this region ends up being a curve that we can parameterize in a finite number of smooth pieces. So now kind of the last part in there, what do we really mean by a positive orientation? Well, a positive orientation is really just a convention that we're going to use so that the region D will always be to the left as we are tracing out the boundary. So if we imagine that our region D is here, we're tracing this curve around the outside, then what's happening is we're doing this, that our part of our region D is always going to be at our left hand as we're going around. So you can kind of think of this as we're tracing it out counterclockwise, if you want to think about it that way. And then we can have the negative orientation where we're tracing it out clockwise so that the region is always to our right as we're tracing it out. So this kind of gives us, if we go back to the beginning now with Green's theorem, kind of going back through and rereading it after some of those concepts. So if we let C be a positively oriented, piecewise, smooth, simple closed curve, so we know simple closed curve, no intersection points, it looks like a loop, ending point is the starting point, piecewise smooth, the boundary can be parameterized by a finite number of smooth functions, and now we've got an idea of what positively oriented means. So with all of those kind of concepts that show up there in our hypothesis for this thing, then if P and Q have continuous partial derivatives on an open region that contains D, so they're nice in a region that in a slightly bigger region than the region we're actually interested in, then and the curl of our vector field is actually gets pulled back to the line integral of that vector field around the boundary. And so in the next video, we'll kind of take those concepts, explore them a little bit deeper, and kind of tear into this. And I will wait and see you guys next time.